Hello friends, welcome back to our Control Systems Simplified series. Today we'll discuss about frequency response and specifications. We have already discussed time response analysis of the control systems and what are the time domain specifications of the second order. Now we will see and discuss the frequency response analysis of the control systems and the frequency domain specifications of the second order control system. Now we need to understand what is frequency response. Now this can be, as we know that this is two types. One is transient response and the second is the steady state response, right? We know that the transient response can be found out using the Fourier integrals. But the steady state response of the system for an input sinusoidal signal is known as the frequency response. Okay, we'll focus mainly on the steady state response here. So if the steady state response of a system for an input sinusoidal signal is known as the frequency response. When a sinusoidal signal is applied as an input to a linear time invariant system, then it produces a steady state output, which is also a sinusoidal signal. Input and output sinusoidal signal have the same frequency, but the different amplitudes and phase angles. Now, if we take the input signal B, R of t is equal to A sine omega naught t, the open loop transfer function will be G of S is equal to G of j omega. Now, we can represent G of j omega in terms of magnitude and phase angle, where G of j omega becomes modulus of G of j omega angle of G of j omega. Now, if we substitute omega is equal to omega naught in the above equation, we get G of j omega naught is equal to modulus of G of j omega naught with an angle of G of j omega naught. And for this, the output signal is C of t is equal to A is the amplitude into G of j omega naught modulus of G of j omega naught, which is nothing but a amplitude, modulus of the magnitude of the signal, then sine of omega naught t plus angle G of j omega naught is the phase angle of the. So the amplitude of the input sinusoidal signal is obtained by multiplying the amplitude of the input sinusoidal signal and the magnitude. G of j omega at omega is equal to omega naught. The phase of the output sinusoidal signal is obtained by adding the phase of the input sinusoidal signal and the phase of G of j omega at omega is equal to omega naught. In that, capital A is the amplitude of the input sinusoidal signal and omega naught is the angular frequency of the input sinusoidal signal. Now we can write angular frequency omega naught is equal to 2 pi f naught, where f naught is the frequency of the input sinusoidal signal. Now similarly, we can follow the same procedure for closed loop control system also. Now let's see the frequency domain specifications. The frequency domain specifications are broadly resonant peak, resonant frequency, and bandwidth. Now, if we consider this in the graph, we can do it mathematically also, but let's understand this more of a graph, more with a graph, so that we avoid the complications of mathematical equations. So that for the better understanding, if this is the response of the system, the resonant peak is the MR, which is nothing but the maximum value of amplitude. MR is nothing, resonant peak, one frequency coefficient, domain coefficient. Resonant peak is nothing but it is the maximum value of amplitude, which is appearing for the first time. Then resonant frequency omega R, which is nothing but the frequency at which the peak resonance occurs. So MR is the resonant peak and omega R is the resonant frequency is nothing but the frequency at which the maximum peak resonance occurs, MR occurs. Then the third one is the bandwidth, and bandwidth is the frequency at which the amplitude drops to 70.7% of its zero frequency value. Right? Its zero frequency value is 1, and if it falls 70.7% of it, and this is exactly what, and this is the bandwidth. So the bandwidth is the frequency at which the amplitude drops to 70.7% of its zero frequency value. So these three are the frequency domain coefficients, which you can explain with the help of this graph, where on the x-axis we have omega, angular velocity, and on the y-axis we have the magnitude, modulus of m of j omega. Okay, and for this, if we have this graph, we have the resonant peak and resonant frequency and the bandwidth, which is nothing but 70.7% of the thing. So MR denotes the relative stability of a stable closed loop system. The peak resonance always indicates, resonant peak always indicates it is the relative stability of a stable closed loop system. A large MR corresponds to a larger maximum overshoot of the step response. So the desirable value of MR is always 1.1 to 1.5. Okay, so we are not expected to have a very large MR, because in that case the overshoot of also will be high and it will take longer time for it to reach steady state value. Then the bandwidth gives an indication of the transient response properties of a control system, because this is where the transient properties die away before it comes to the steady state value. So a large bandwidth corresponds to a faster rise time, and bandwidth and rise time are inversely proportional. A larger, faster rise time, bandwidth and rise time are inversely proportional. So bandwidth also indicates the noise filtering characteristics and robustness of the system. Increasing the natural frequency increases the bandwidth. So bandwidth and MR are proportional to each other. If MR peak resonance peak is more, naturally it will take a longer time for it to reach the 70.7% of its zero frequency peak. So because of which the bandwidth is also will be more. So if resonant frequency is more, bandwidth of the control system is also more. And so that's exactly what about the concept of a frequency response and frequency domain coefficients, right?